Snezhana for letting us present our work. This is a team's effort. I'm a presenting author, Alexei Chekhlov. This team, all team works for Dassault Systemes, which is in a Boston, US headquarters of a much larger French engineering software company. And one of the products of Dassault Systemes is a product called Power Flow, which is one of the probably highest quality commercial implementations of the so-called Lattice Boltzmann method. But we are most of the time working on very particular, not very theoretical, but very specific cases related to practice. And this is a unique case when we actually, we believe we did some advancement that relates to theory and the advancement of the method itself, and we wanted to share the results of this with you. The team is headed by Hudong Chen, that is the last name here, who should really be the first one, because he is the name has been known in the field of Lattice Boltzmann for many, many years. He was a spiritual leader behind many theoretical papers related to this and various advancements of this in the past, dating back to early 90s in Los Alamos and many other places like this. Given the fact that some of you know this subject very well, but some of you don't know anything at all about Lattice Boltzmann, but I assume you all love and know physics, I would like to give you a little bit of positioning. Where is this positioned in the grand scheme of physics? So we're talking about dating back to 1916, 17, to the asymptotic multiscale methodology, which was called Chapman-Enskog procedure, which attempted to derive the continuous equation of matter from statistical mechanics Boltzmann equation. And in fact, a very little tiny example of similar things was done by Albert Einstein around 1905 when he derived macroscopic properties of the Brownian particle from microscopic properties. So you can think of that methodology as much more complex and much more realistic attempt of doing the same thing. So the method consists of some assumptions, such as time separation of time scales, like collision time, much smaller than external time scales, and under these assumptions, the Boltzmann equation can be solved around the equilibrium solution, which simply equates the collision term to zero, which leads to the Gaussian distribution function. And this is equivalent to an expansion in so-called Knudsen number, which also may be related to much better known numbers like Mach and Reynolds, approximately Mach divided by Reynolds. A Knudsen number you can think of as a mean free path divided by some physical characteristic length. So anyway, this is a purely theoretical asymptotical methodology. Now, how is it related to numerical schemes? From the early 70s, attempts were made to map it into numerical methods. The first bunch of attempts, probably from the early 70s to the 80s, mid 80s, and 80s, depending how you want to judge it, were the growth and lifespan of so-called automata, lattice automata methods, of which there's several. Pamot and Uriel Frisch were the names which were associated with these things. And they were the first step to map basically Chapman-Enskog procedure into the numerical, purely computational physics procedure that will allow you on a computer to solve an actual system. So these first attempts were very popular. Many very smart people were involved with this and were very excited. But then the interest kind of dissipated, And in the early 90s, an upgrade of that methodology took place under the name of Lattice Boltzmann method. I think the first really solid paper in 1993, 92, and then towards 97, 98, a full analytical background was developed, of which Hudong Cheng is one of the authors, by the way. Around 1998, he published with Gary Doolin one of the papers which laid out foundation to this. Okay, that's the subject of today's discussion. This is in the past. So the LBM, Lattice Boltzmann method, took a strong hold since those early to late 90s. So much so, because I am sort of from those years, my graduate school is 91 through 96, we were mostly taught finite difference methods, but by the end of this, and towards further and further, Lattice Boltzmann method were realized to be much more accurate, much more faster because they're parallelizable, they're local, and they also can treat much more difficult physical situations, including multi-phases, interfaces. It's a lot more flexible and fast method. And so anyway, right now, this is probably, you can say, the most accurate and the dominant method as number one, probably, and the finite difference methods that at least we used to be taught kind of go behind this. Okay, so now the classical LBM as it is used, and there are very thick 1,000 pages books written about this, they're all mapped into the Cartesian geometry. That means the cells are rectangular, whether 2D or 3D, and the particles move exactly from one cell to another along the straight line paths, which is the beauty of this method, because this allows the advection part of the operator of the Boltzmann equation to be precisely modeled. The numerical dissipation, which typically happens if you do finite differences, virtually absent. It may come from different reasons in small amounts, like from boundary conditions, for example. There are all these nuances, but strictly speaking, it's almost perfect. There's almost no numerical dissipation. That's the beauty of it. And it also is local. That means you can parallelize it as much as you want. That's the starting point where I'd like to start. Sorry that I spent some time explaining this. So now the evolution of LBM is definitely at saturation stage, and it's widely used in commercial applications. What's the problem with it? The problem with it is that it is Cartesian intrinsically. There is no very well defined and tested and validated generalizations of it onto the curvilinear cases. Why would you need that? Well, the real applications like, I don't know, turbines and propellers and things like that are intrinsically curvilinear. And even if you look at simple geometries, if you are interested in boundary layer problem, that's the difficulty, because there the solution changes very rapidly, and you cannot treat it with equidistant grids, just no way. The poor man's solutions that LBM offers, even in commercial applications, is the so-called VR approach, where they would just double and double and double, and you can define how much of these VR regions you can do approaching into your boundary layer. But this is still, I think everybody would understand that this is not perfect, right? Sometimes you would have a lot more control over this. And this is where a curvilinear formulation of Lattice Boltzmann method can be extremely useful. In fact, boundary layer problem is probably where finite differences are still competitive to LBM. So thus this work. So Hudong Cheng, in the paper that he published, which I refer here as paper number 1, published a theoretical justification for generalizing the LBM method into general Riemannian geometry, following tensor formulations of equations of motions. And this paper exists for out there for about a year and a half to 2 years. And it was, even though it was written, it was still not clear if it has validity, because there's so much approximations involved, asymptotical assumptions. We wanted to create a full-fledged validation study of this method on the particular cases where we would implement this. Well, that's where I come in. I wrote the code, I re-derived most of the formulas, I came up with exact solutions, I mapped them, and I put this all together. The idea is to validate this method. If this works, this may take the LBM approach to the next level, make it curvilinear to describe very complex geometry in general, and also zoom into the boundary layer with as fine resolution as you want. And that will make it truly competitive to any finite difference method. That's the general idea. Okay. So what do we want to do here? I will not have the conclusions part, because my conclusions will be right here. So the theoretical paper by Houdon will be tested here. It is the first time use of truly curvilinear tensor formulation of the Lattice Boltzmann method. Okay, it relies on volumetric approach. That means instead of looking for density functions, we're going to be looking for n, the number of particle function, which includes the area of the cell, and it kind of hides the curvature of the space in it. And here's the key thing, and I'd like things very, very simple. The first law of Newton says that if body has no external forces, it will continue moving with a constant path, with a constant velocity. So the only reason that may force it to deviate from the constant path is the external force. And that is why the theoretical implementation of such method can be done by formulating the external body force that will enter the curvilinear formulation of equations that will make and lead to the exact momentum and momentum conservation and reproduce the Navier-Stokes equations in the viscous order. And that is what we are attempting to show here. Some pieces of the Houdon's theoretical work to describe how curvilinearity is actually introduced into the system. I think the bright observation that he introduced is that he wants to, as opposed to general Riemannian approach, he wants to introduce it discretely. For example, what you see here is a definition of the tangent basis vector along the ith direction, and it is done, as you can see, as a finite difference, okay, which is the right-away mapping into the grid, right? So the method, this is a computational physics into the grid right away. Now, but it is all stands on the assumption that there is a Riemannian mapping between the true curvilinear space X, where we live right now, and we're going to map it into the space that resembles the ideal space for the LBM as it is now. I call it Q space here. That space will be equidistant. In fact, the distance between the nodes, you can think they're 1 from each other. And so we assume that such mapping exists, and it is not degenerate in the sense of differential geometry. For example, the basis vectors, which can be defined everywhere in that mapping, never are collinear, right? So that mapping, therefore, will exist. And so then the logic goes, this mapping exists, we're going to take one particular point in that space, we're going to find its neighbors, and for each point and its neighbors, we're going to define the tangent basis vectors, GIs, and that's schematically, I'm sorry, maybe it's not perfectly done, but so this is the idea, this is the true X space, this is the ideal Q space, and the transformation is this transformation X. All right, and that will lead to a new way of understanding of LBM. Instead of particles moving from ideal square cells to another ideal square cells along straight paths, my particles or our particles will move along curved paths. Okay, here's how the attempt was made to make this work before. All right, without the generalization using tensor formulation, they were moved in the curvilinear grid like this along straight paths, and then the attempt was made to interpolate to the new center of cells points, and that instantly leads to a new dissipation. So this method will be similar to the ideal LBM. There will be no dissipation. Particles will move along curved paths, and we're going to introduce all the necessary terms in the equations to make this work. So thus defined tangent basis vectors will imply the metric tensor Gij subscripts, and using the scalar products. It will also define the volume or the area, if it's 2D, of the curvilinear cell, which is parallelepiped in 3D, or some sort of curved square in 2D. Using this, we can then go and define cotangent basis using standard notations that are very well known, using Levi-Civita symbols. And in this way, tangent and cotangent are related perfectly through the Kronecker delta. And these will be helpful to us to write the equations of motions. For example, the first thing we can do, we can redefine the new, what is called speeds in the language of LBM, or the velocity vectors, local velocity vectors, with which particles will move in the following way, that you see here, using the dependent on space tangent basis vector. All right, Christoffel symbols, which are a little twisted Christoffel symbols, because they are discrete. The ideal Christoffel symbols will have the partial derivatives here. This is a finite derivative here, can be defined. And now we are ready to rewrite the Boltzmann equation using all of this apparatus that was built. But there is a new term in it, which is this term. That is the term. I would like to call it a force. It looks like a force here, but it's not really a force because these are particles, number of particles. So this is the term that is related to the external force that will be the body force that will compensate for particles moving along the curved trajectories from cell to cell. Anyway, if you do this, now we need to finish explaining the algebra, how this is related. So this is how the particle distribution functions are related to the n, the number of particles. That's the essence of the volumetric method, using the area of the cell or the volume of the cell. Using this, we can now relate the measurables of our system like density, velocity, as moments with respect to the local speeds E alpha, just like in the classical LBM. And in this formulation, we're going to be using the simplest linear one relaxation time approximation for the collision operator that you see here. Everything works fine without any more complexities. And here is how the new LBM can be proposed. Very similar to the classical one, but with, again, body force. The body force will be part of this. So if you're inside of one particular cell, the particles flow from that cell to the neighbors. That's how it changes momentum. And from the neighbors into that cell. So you need to write a balance. So these are into the cell from the neighbors, and this is out of the cell from the neighbors. And this one is post-collide, this is post-advect. So The average of these two will give you the inertial force, which is that body force that we need to make perfect momentum conservation in this curvilinear system. And the analytics detailed in Hudong's paper gives that momentum flux given by this expression and the delta n given by this expression makes the system complete and closed. As he shows there, it leads to satisfaction of Navier-Stokes equation at the viscous order perfectly. Okay, the inclusion of n prime, which is post-collide, and this one is post-collide on this side, makes it an implicit relationship which can be resolved by either splitting previous time step on the next step or iterative procedure that can be done and just doing some iterations to resolve this. And this completes the formulation of the model. The F-eq, the equilibrium distribution function corresponding to this case in totally curvilinear case is given by this fairly complex expansion, which is really a double asymptotic expansion, first in Knudsen and second in Mach number, and it can be derived, but it's rather involved, as you can see. And ultimately, we can calculate the density and the velocity that are the measurables of any fluid flow. So all I want to do right now, and I'm going to go a little over time, a little, not too much. I'm going to show you my implementation of this for four two-dimensional problems with various types of curvilinearity embedded into them, strong, all cases are strong, and they have exact analytical solutions. These three problems are very well known. This fourth problem was created by us, analytically solved by us, by me actually, and we solved it on converging grids, on highly increasing in the resolution grids, and show how the results work. All these problems were solved numerically as non-stationary problems converging to a steady state from zero initial velocity state. Convergence was judged by total kinetic energy and total angular momentum. In case of circular, two problems 3 and 4 are circular. So in those cases, we also used angular momentum as to the single precision accuracy. Okay, these are the two lattices that we used. And maybe this is too much details, you might say, but they are not, because the fact that, I have two lattices here, it's making a big difference, because this is a more standard lattice that more or less everybody is using for LBM, and I had to use it because everybody is knowing and using it. And this is the one that is a lot more complex, it's longer, its stencil is 3 times larger, as you can see. So particles go not just to the neighboring cells, but to the cells twice as long from the center. And the reason I'm using, and this is the easiest and the smallest lattice for which truly curvilinear cases would work. And the new result that we did not know it will happen, we uncovered it during this work, is that namely from this lattice and higher order lattices than this, the symmetry, rotational symmetry sufficient to reproduce the Navier-Stokes equation can only be recovered. Anyway, we covered the cases equilibrium, tau equals to 1, and strongly non-equilibrium cases here as well. Let me just quickly show you. Okay, so the very important result is that, again, there is a degree of isotropy that can only be done from a certain level of lattice and higher, and not from the ones that are currently used for Cartesian LBM. So these are, by the way, the isotropy conditions. So the method that's currently used only satisfies the first 3. The high order lattice satisfies 4 conditions, and only on them the curvilinear solutions are reproduced. This is a trivial case, of course. School, any fluid mechanics course has this. We have complicated this case with lattice converging of making small steps towards the walls. Okay, and the step is, so this is Cartesian case, but the steps are non-equidistant. In this case, this is an example how it looks like. You can see these cells are probably 3-4 times smaller than these cells in the middle, and we solve it numerically from very small resolutions to high resolutions. From about 128, you visually cannot distinguish the numerical and exact solution, both for density and for the profile of velocity, which is linear in this case. And these are two lattices, D2Q9, that's the one that's widely used right now, and this is D2Q21, which we believe should be used only and higher for curvilinear cases. So in these Cartesian cases, there seems to be no difference between them. Now, these are cases with tau between 1/2 and 1, which are strongly non-equilibrium cases. Okay, convergence is very, very well. And in other cases, equally similar, very, very well-known Poiseuille flow in the pipe. Again, my cells are reduced to the walls, thus resolving the boundary layer better. And convergence is very, very high quality. There's no difference between D2Q9 and D2Q21. However, this is where the new things start. So these are truly curvilinear cases, circular Couette, and then circular Poiseuille after that. They have exact solutions. This is a better known part of it. The lesser known part of it, by the way, this is how the geometry looks like. The area of the cell, this is strongly curvilinear case. R2 divided by R1 is 11. That corresponds to area of this cell is 11 times larger than this one. And this is how profiles of velocity look like in this case. But we also need to compare the density, because this is a weakly compressible case, analytical exact solution, and comparisons. And this is where the astonishing to us result came up, is that D2Q9, due to lack of isotropy, is not converging to the exact solution of Navier-Stokes. It is actually converging to something which is not Navier-Stokes. And only the next level of complexity of lattice, which is D2Q21, which you see here, is perfectly converging for all measurables. This is rho, and this is the radial velocity, which should be 0, and this is the azimuthal velocity, which has non-trivial profile, perfectly converging to it with still low resolutions.
I think we'll have to leave it at this now.
Yeah?
Because we are
okay, all right.
Almost 4 minutes over.
Anyway, so the other one does exactly the same thing. And this is our proposal for the next step of our Lattice Boltzmann method in curvilinear coordinates. Thank you very much.
Thank you. And we'll leave, first of all, thank you.